Alright, in this part of the video, we are going to look at another balanced tree. It's called a 2, 3, 4 tree. So in 2, 3, 4 tree, let's take a look. In 2, 3, 4 tree, it could have two nodes. Like if I have a 20 here, this is a two nodes. I can have at most two children there, and I could have, for example, I could have a three nodes. A three nodes, at most it it could be a leaf, but at most it could have three children there. And I could also have, okay, this is two nodes, three nodes, this is called four nodes. Four nodes can contain up to four children there. So that's called a 2, 3, 4 tree. 2, 3, 4 tree, just like a binary search tree and a 2, 3 tree, the left child will be less than this smaller one, and you get the idea. So it's very similar to the binary search tree idea and the 2, 3 tree. So now let's take a look at what's the difference between 2, 3, 4 tree and the 2, 3 tree, other than the number of items a node can contain. Let's see. So I'm going to add the same set of data, still the sorted version. Remember, when you have 10, 20, 30 inserted in a binary search tree, your tree is out of shape pretty soon. But when you insert it into a 2, 3 tree, it's always balanced. The way you do the way you do that is to, as you are adding something, when the node is getting crowded, you split the node going up, and your height is always increased or be decreased at the root level. Alright, now let's do the same operations for 2, 3, 4 tree. So I'm going to add 10. Let's see, add 10. Okay, add 20. That's no trouble. And add 30. Still no trouble. Remember, a 2, 3, 4 tree can contain, each node can contain up to 3 data. Okay, now here's the difference. When I try to add 40, I come in here and I look at, even before I add 40, I look at this and say, oh, it's too crowded. It's too crowded. I'm going to split it right here. So even before you add the data, when in the 2, 3 tree, when you come across a data that contain a node that contains 3 data, you're going to split it right away. Alright, so we split it right away and we add 40. Right, similarly we come in, then we add 50 here. When we are trying to add 60, it comes here and say, already too crowded, I'm going to split it. So even before you add 60, you're going to split it, and this is the tree you got so far. And similarly, you can add 50, then you add 60, then you add 70. Now let's see. When I'm trying to add 80 here, I'm trying to add 80, so I'll come down here. This node is alright, not too crowded. Then I come down here. Oh, it's too crowded. I'm going to split it before I add 80. So this is what you got: 20, 40, 60, and 10, 30, and 50. And 17. Okay, so this is what you got. So you split the node, and this when you're trying to add 80 here, let's see, when you're trying to add 80 here, but it come across this node, they say, no, that's not going to happen because it's too crowded. I'm going to split it right now, right here. So you're going to do this. Now when you add 80, you just go ahead and do that, add 90 and go ahead and do that. And if you're trying to add 100, you come here, you have to split and move up. So that's how you do 2, 3, 4 tree insertion. And as we can see, the algorithm is different from 2, 3 tree by, while it's going down to the leaf where you're trying to add. Whenever it comes across a node that's too crowded, which contains 3 data, it will split it right there. So it won't work like 2, 3 tree, like after I insert something, I found it's too crowded, I'm going to go back up and split, maybe go back up again, split, then increase the root. This one is one pass. So as I'm going down, whenever I encounter something that's too crowded, I'm going to split it right here. So once you're there at the leaf, it's guaranteed you will have space for the new node. So that's the difference between 2, 3 tree and 2, 3, 4 tree. 2, 3 tree requires two paths, possible two paths, like going down, then back up, splitting. But for 2, 3, 4 tree, it's always one path. Like as I come across you, I'm going to split you right away, even if I'm not inserting here. So that's a big difference between 2, 3 tree and 2, 3, 4 tree. And you might think, so as you can see, because 2, 3, 4 tree, each node could contain at least 3 data. So the height might be smaller than the 2, 3 tree. But the height isn't the concern, isn't the big concern here, because both tree, 2, 3 tree and 2, 3, 4 tree, they're balanced. So that's what's important. And the decrease the height of 2, 3, 4 tree, it seems like an advantage because we know our performance is directly related to the height. But you have to take into consideration at individual node. Like for example, when I look at this node, this for node which contains 3 data. At the individual node, when I'm trying to search or add or delete, I have to decide which way to go. That's more comparison. Do I go this way, or that way? So that's more comparison than 2, 3 tree. So the advantage of 2, 3, 4 tree isn't the decrease the height, because that one is kind of get counterset by the number of comparison, the increased number of comparison. The advantage is a one pass, so it only does one pass on its way to for insertion. Now let's take a look at the deletion algorithm. So how about I'll give you one example that look like this. So like a 40 pretty empty 2, 3, 4 tree. Let's see, 10, 30, and 50. Then you will see the deletion algorithm is just the opposite process of the insertion algorithm. So remember, the insertion algorithm, we come all the way down, but while we if we encounter something that's too crowded, we are going to split it right away. So similarly, for deletion algorithm, you start from the root, and you see, if it's a 2 node, in our case that is, it's a 2 node, that means not good, it's not crowded enough. If I'm deleting something, I might be in trouble. So what you do is, on your way down there, whenever you encounter a 2 node, you're going to do a merge. In this case, this is a 2 nodes, I'm going to do a merge here. So even before I reach the leaf I'm trying to delete, again, the delete algorithm is just like a binary search tree. You find the in-order successor, and you always delete the leaf. So we always delete the leaf. So here I'm going to merge the tree because I encounter a 2 node, and that could be trouble when later on when I delete something. So you just merge it right away. And now after you merge it, if you're trying to delete 90 here, you come down, you say delete 90, no problem. Just 90 is gone. You come here, if you delete 80, it's gone. And if you come here, you want to delete 70, you take a look, you say, no, that's a 2 node. I'm going to do the merge. So you're going to merge it, and the merge result will look like 20, 40. So you're going to decrease one child and move down the data. So then you see if 70 is gone, go just delete 70. So it's a totally opposite procedure as insertion. For insertion, as you're going your way down to insert it as a leaf, you split as you're going down, and deletion is as you're going down to the leaf. For the deletion, you merge as you're going down. Again, 2, 3, 4 tree will give us log 2 to n performance. The decreased height isn't the objective. The objective is a balanced tree, because the decreased height, like when you compare 2, 3, 4 tree and the 2, 3 tree, the decreased height also give you the overhead of more comparison at each node. Thank you.